This is 6.4. We are going to look at the big idea here about math and how everything that you learn along the way from kindergarten up until your senior year calculus, you learn about something. Take, for example, addition, and you learn the opposite of that, the thing that undoes it. So subtraction. You learn multiplication, and then you learn about division. You learn about squaring something, and then you learn about taking the square root, undoing a square. There's cubes, cube roots, and so on. You learned in geometry last year about the sine of an angle, and you can use sine inverse to undo, okay, to essentially cancel out. Well, what we're going to look at today is that if you have a function, f of x, in most cases, especially in Algebra 2, there is a function f inverse, f to the negative 1, that will undo it. So let's talk again about the function machine. First off, if you are taking function f, you input x and it spits out some f of x. Well, what an inverse is allowing us to do then is to take that output, plug it in, f inverse, a negative 1, just like sine, f inverse undoes that thing and spits you out exactly what you put in back at the beginning, which in our case is x. So every function, for the most part, can also have a function inverse that undoes it. So let's talk about this. We've got function f, and the way that I like to think about these is you put your socks on and then you put your shoes on. And so when you get home from school, you have to take your shoes off and then your socks. Okay, so you have to go in reverse order of things that happen. If we look at the input here, the first thing that happens is you multiply by 4. Then we add 1. So this is like, if I stick with the analogy here, multiplying by 4 is your socks, and adding 1 is the shoes. Okay. Well, G, to undo that then, you have to take off your shoes first. So what is the opposite of add 1? Well, you have to take your input and you have to subtract 1. Then you need to do the opposite of multiply by 4. Take off your socks, which is divide by 4. So let's test it out. Let's see. If we take f of 3, what do we get? Well, 4 times 3 plus 1 is 12 plus 1 is 13. If we take g of 13, we should get back out 3. Well, let's see. Plug 13 in. I've got 13 minus 1 over 4 is 12 over 4, and we get 3. So it completes the circle. It goes from 3 to 13. 13 gets plugged in, and we end up back where we started at 3. The sock-shoe analogy doesn't work forever because we can have more and more and more operations or things happening to a function. So one of the easiest ways to do this is to rewrite this. Remember that f of x just stands for your output. So that's y, 2x minus 5 over 7. And all an inverse really does is it switches what you are inputting and what you are outputting. So that's what we do. We can switch x and y because x and y stand for input and output. They don't have specific meanings. They just literally stand for input output. So we can say, well, x equals 2y minus 5 over 7. And now we solve for y. This will force us to do everything that we need to in opposite order. Okay, so by solving for y, you can't divide by 2 you have to start furthest away and work towards it. So you need to multiply 7 both sides. So we'll multiply this side by 7. That cancels out. We have 7x equals 2y minus 5. Then you need to add 5. And I'll take that up over here. We have 7x plus 5 is equal to 2y. And then we need to divide both sides by 2. And now our inverse function, 7x plus 5 over 2. Now you can see the parallels here. If you are going on the journey of x gets multiplied by 2, then it gets subtracted by 5, then it's divided by 7. So the very last thing that happens is dividing by 7. So the very first thing that needs to happen with our inverse is multiply by 7. All right, well then keep going backwards. It was subtracted by 5, so we need to divide by 5. Add 5. And then the very last thing is this division by 2. And so they are inverses of each other. How about we try one more here? This one is a little bit simpler, though it's a fraction in front. Just consider h of x as this is really my input. It's equal to 2/3 x minus 4. We're going to trade our input and our output, so I turn this into x equals 2/3 y minus 4. And we need to solve for y. We need to force ourselves to go backwards. So we add 4 is the first thing that we do. And we have a 2/3 y. And to get rid of a 2/3, the easiest thing to do is to multiply by the reciprocal. So I'll put a parenthesis around this. You got a 3/2 here, a 3/2 there. Those cancel. Leaves us with y equals 3/2 times x plus 4. And so you have to have that parenthesis there. You could distribute the 3/2, not really necessary. To verify that something is truly an inverse, you're going to do function composition, something that we've talked about in the previous videos. And you just need to essentially show that f and g, just as we talked about in the introduction, the inverses truly undo each other. So you do the function composition in both ways. So let's see, what is f of g of x? Let's compose those. Well, you start with f, so it's 2 times your input minus 5 all over 7. Okay, well, g is going to go in our input, and so in this space I have to put g, which is 7x plus 5 over 2. So I will do 7x plus 5 over 2. And now we just want to make sure we carefully see that everything cancels out like it should. So the first thing that would happen is the 2's would cancel. And so we would be left with 7x plus 5 minus 5 all over 7. Simplify that by eliminating the 5's, simplify the 7's, and you've got it part way verified. On the other side, we need to do this in the reverse order. It has to work both ways for an inverse to truly work. So g of f of x. Start with g, so you've got 7 times your input plus 5 all over 2. This time we're going to input f, so I go 2x minus 5, 2x minus 5 all over 7. And I begin to just cancel things out. You're really just kind of proving it. You're not really discovering anything. So you're canceling the 7. That would turn this into 2x minus 5 plus 5 over 2. 5's cancel, 2's cancel. And you see that we have just x. And therefore, it is in fact verified. Inverses can do a lot of things, and you have to remember the inputs and the outputs. In this equation, you are inputting Fahrenheit, and you are outputting Celsius. So this is how we convert from Fahrenheit to Celsius. Well, what if we want to convert the other way? Okay, what if you live in pretty much any other country and you have Celsius and you want to convert it to Fahrenheit? Well, we need to swap the inputs and the outputs, and that's what an inverse does. Now, if the variables mean something, that's what this text says here, just beyond x and y, standing for input output. You can't just switch them. So it would not be fair just to say, oh, here, put a c there, put an f there, and now you've got your inverse. You need to just solve for f. Okay, so we need to take this and we need to solve for f. So I start with c equals 5/9 times f minus 32. And the very first thing we need to do is multiply by the reciprocal to get rid of this fraction. So I've got 9/5c is equal to, those things cancel out, f minus 32. And then finally, we just add 32 to both sides. So our function now that will convert Celsius into Fahrenheit is going to look like this. 9/5 Celsius plus 32. So when the inputs actually mean something, you can't do that switch. We're allowed to do that with x and y because they just stand for input-output. And that's really what we want to do. There is a little bit of a trouble with some functions. We'll talk more about this a little bit later, but this function looks like this. It's a parabola shifted down 9. And the problem with this is that if, let's say, you input 3, you get out, plugging in 3 squared is 9, 9 minus 9 is 0. But if you flip that around and in the inverse you input 0, there are actually 2 things you could get. See, what squared minus 9 will give you 0? The answer is 3 or negative 3. See, you've got 2 values here where the function is 0. And so this is a problem. So what we have to do is we have to limit. We have to say, you know what? X is going to be greater than or equal to 0. Now we can find an inverse. We can say flip them, x equals y squared minus 9, add 9 to both sides, x plus 9 equals y squared. Take the square root, and since we know that it's going to be positive, we don't have to have the plus or minus. We can just simply say x, the square root of x, plus 9. Normally you'd have to have plus or minus, but when we limit our values to only being positive, we can then just say my inverse is only going to be the positive. If we flip this around and we said find the inverse when x is negative, less than or equal to 0, then we would say y equals negative square root of x plus 9, because we'd want to go backwards to the negative side. Okay, 5 question homework assignment with this one.